Hi everyone, we are presenting our CPE 185 final project. Our team name is 1X and the topic for our project is heart rate monitor circuit and data output. So for our final project, we created a heart rate monitor circuit and each person had their duties divided. For example, Brandon Syra, he was responsible for constructing the physical heart rate monitor circuit and peak detector algorithm. Pratham Sali, he was responsible for calculating the time difference and the moving average. And Jesse Hernandez, he was responsible for calculating the beats per minute. And Nyarka Manas, she was responsible for displaying the beats per minute. And all of the team members, they were responsible for data logging and creating the test cases and generating the code and creating the finite state machines.
Next, we have our finite state machines, and to start off our finite state machines, we have our reset. Once it starts or resets, we have our heart rate sensor hardware. The hardware is going to output to our STM board, and this is going to go first into our finite state machine where we have our peak detector algorithm. If we have no peak, we're just going to loop back on itself until we do have a peak. If we have some error, like no output, we're just going to output error. Next, we got to calculate the time difference. For this, we would need a peak. Now, if our peak is less than 5 data points, it's going to go back to our peak detector algorithm, and it's going to keep doing this until we have more than 5 data points. Once we have more than 5 data points, or greater than or equal to, we're going to go on to stage 3, which is our moving average. After our moving average, we're going to go to BPM, which is beats per minute, and then we are going to display these results. Then we go back to our peak detector algorithm, and we are going to do this again so that we can display different results.
First, we connected a low power supply to our heart rate circuit, and our heart rate circuit was comprised of an IR LED and photo transistor. We also had an amplifier, an active low pass filter, a final amplifier with the low pass filter, and a potentiometer. And then this would output to the STM board. We used the A to C input pin, and then we ran a peak detector algorithm, time difference algorithm, and moving average algorithm. And then we use those 3 algorithms to be able to compute the beats per minute and then finally display the BPM.
Next, we look at test cases. So the first test case that we are going to look at is the circuit. After much debugging and rearranging of our circuit and tweaking the waveform settings, an output was displayed to our scope. A test case for this, one that we used initially, was displaying it in a very bright versus a very dark room. Now, if the light wasn't terribly bright in the room, so like my room, it didn't make too much of a difference, so we didn't change too much when we were testing it like that. We tested different kinds of gains for the op-amp to shorten the peaks, and also applied a DC input to the last positive input of our op-amp to raise the output voltage. This was to move the voltage above 0 volts, but still be below 3 volts so that our STM board could read the results. Now, the peak detector algorithm was not tested much, but that was because it was a little bit more complex than anticipated, and we were not able to test that.
So for the test cases for the moving average, here we have 2 snapshots of two different sample of data. Here for testing the moving average, we just used a basic for loop that calculates the sum of the data that are present in the data array, and then we divided with the data points, that was 5, to get the required moving average.
In order to calculate the BPM, we needed to pass the moving average as a parameter, and the moving average was given to us as seconds per beat, and we needed to change that to beats per second. So we needed to take the inverse, which would be 1 over the average, and in order to get beats per minute, we needed to multiply by 60, so then the final beats per minute would be 60 divided by the average. And for my test cases, I first used an average of 3, which gave me 20 beats per minute, and an average of 1, which gave me 60 beats per minute.
The display had 2 cases. For the first test case, we had deleted one of the 2 lines of code from Lab 5 to be able to display only 1 line of information. We also deleted the infinite while loop to make sure the information only prints once. For the second test case, we added in a delay to make sure only the implemented code in STM displays, not what was already programmed into the Nucleo board before. After the second test case, we were able to easily make all the necessary changes required to display the BPM. To conclude, our project is unfinished. The code did not go well together in a FSM, and if given more time, this would be what we need to work on. Individually, our parts work or appear to work as intended. A way to advance this project is to have an LCD screen display our data and store it in memory and compare it to other people or other situations where heart rate may change.